Have you ever stopped to think about the invisible forces that shape our world? Well, today we're diving into two of them. We're talking about a couple of unseen giants that power our farms, our cars, and even our cameras. But to make them, we have to master some seriously extreme temperatures and solve some pretty clever chemical puzzles. So let's get into it.
Okay, so this sounds like the start of a riddle, right? Farming, photography, and explosives. I mean, on the surface, what could they possibly have in common? But, it turns out there's a single chemical thread that ties them all together.
And the answer is two incredibly powerful, mass-produced acids, nitric acid and sulfuric acid. These are the true unseen giants of our modern world. So what we're going to do is go on two separate journeys to see the incredible engineering it takes to create them. First up, nitric acid. It's made using something called the Ostwald process. And for this one, the name of the game is speed and heat. We're going to see how you transform simple gases into a powerful liquid with just incredible efficiency. Every great recipe starts with a shopping list. And for nitric acid, the ingredients are surprisingly simple. All you need is ammonia gas, the oxygen from plain old air, and water. Yep, that's it. The whole thing really happens in three main stages. It's basically a series of oxidation reactions, which is just a fancy way of saying we're strategically adding oxygen at each step. First to the ammonia, then to the gas that creates, and finally, we absorb the whole thing in water. Let's see how it works.
Whoa, so the first step is intense. We are talking about heating a mix of ammonia and air to around 850 degrees Celsius. To put that in perspective, that is hotter than the surface of Venus. This crazy heat is what really gets the reaction going.
But even that intense heat isn't quite enough on its own. The real secret ingredient here is the catalyst. It's this mesh of platinum and rhodium that acts like a molecular matchmaker. It grabs the ammonia and oxygen and helps them react way, way faster, creating nitric oxide gas. So after that fiery first step, things cool down. A lot. The nitric oxide gas is brought all the way down to about 150 degrees Celsius. Then in a second chamber, it gets another hit of oxygen, transforming it into this reddish-brown gas. That's nitrogen dioxide. And here's the final stage. That nitrogen dioxide gas gets pumped into what's called an absorption tower. Now, this thing is filled with materials that create a kind of chemical labyrinth, which is just a brilliant way to maximize the contact between the gas and the water that's trickling down from the top. It's inside this maze that the gas finally dissolves and reacts to become nitric acid. So what's the result of all this heat, pressure, and clever engineering? You get a final yield of around 96%. Now, for an industrial process on this kind of massive scale, that level of efficiency is just phenomenal. Almost nothing goes to waste.
All right, one giant down, one to go. Let's switch gears and turn to our second acid, sulfuric acid. This is made using something called the contact process. And believe me, it presents a completely different and honestly, an equally fascinating challenge.
The shopping list here is just as straightforward. We start with sulfur, either the pure stuff or from ores, then our old friend oxygen from the air, and of course, water. The real magic, though, is in how you combine them. Okay, so here's the heart of the problem with making sulfuric acid. The key step is turning sulfur dioxide into sulfur trioxide, but this reaction is reversible. And it's exothermic, which means it produces its own heat. The more heat it makes, the more it actually pushes the reaction backward, undoing the very thing you're trying to do. It's a real puzzle. So this creates a classic chemical engineering dilemma. If you crank up the heat, the reaction goes super fast, but you get a terrible yield because it just keeps reversing itself. But if you cooled it down, you could get a great yield, but the reaction is so painfully slow, it's useless for mass production. So, what do you do? Well, the solution is absolutely ingenious. Instead of trying to do it all in one go, engineers break the reaction into 4 separate stages. The gases pass over a catalyst bed, they react, and they heat up. But then, and this is the clever part, before they go to the next stage, they're cooled back down. This step-by-step approach lets them manage the heat perfectly, keeping the reaction moving forward without ever letting it get hot enough to reverse. And just look at the result of that clever balancing act. This multi-stage process achieves an incredible yield of 99%. It perfectly solves that temperature dilemma, giving you both high speed and high efficiency. Just brilliant. So you'd think the last step would be easy, right? Just add water. Well, it turns out that reaction is, and I'm quoting here, violent. It produces so much heat so fast that it instantly boils the water, creating this dangerous, hard-to-collect mist of pure acid. Not good.
And this is where the final piece of ingenuity comes in. Instead of adding water directly to the gas, they first absorb the gas into concentrated sulfuric acid that's already been made. This creates a much more stable intermediate called oleum. Then you can safely add water to the oleum to get your final product. It's a fantastic way to tame a really dangerous reaction.
So we've seen the how, but let's talk about the why. Why go to all this trouble? Let's connect these giant industrial processes back to things we all see and use every single day.
The impact of nitric acid is just immense. It's a key ingredient in the fertilizers that feed billions of people. It's used to make explosives, create chemicals for photography, produce gunpowder, and even to clean metals for welding. I mean, it is everywhere.
And sulfuric acid is just as vital. It's used in a different type of fertilizer. It's the acid inside your car battery. It helps create materials like rayon and plastics. It's a component in our detergents, and it's essential for countless dyes and medicines.
So, what's the big takeaway from these two incredible journeys? Well, for me, it all comes down to this clever balance between pure chemistry and really practical engineering. Yeah, this chart really sums it all up, doesn't it? For nitric acid, the main challenge was all about mastering raw heat and pressure with a really expensive catalyst. But for sulfuric acid, it was about taming a reaction that wanted to run backward, using a super careful step-by-step cool-down method. Two totally different chemical problems, solved with two incredibly clever engineering solutions. From the food on our plates to the phones in our hands, our world is literally built on these complex industrial processes happening just out of sight. It really makes you wonder, doesn't it? What other unseen giants are out there quietly making everything in our lives work?